Ladies and gentlemen, good evening. On behalf of the SCI, I'm introducing and chairing tonight's lecture. But first of all, we just need to deal with a little bit of housekeeping and safety. There are no planned fire alarms this evening, so if there is an alarm, you must leave the building either through this exit or back through the way you came. And the nearest assembly point is on the corner of Belgrave Square, so you'll be directed to the right place from that perspective. And obviously, please do keep exits clear at all times. Just a point of courtesy, really. Please do turn your phone to silent if you have them. If you could check that now, because that's always a nice thing to do. And please don't take photographs during the lecture. It is being recorded and will be viewable, so you can go back and have a look at it. And the event is also being live streamed to other locations and indeed upstairs as well to an overflow lecture theatre as well. So you will be able to see everything in future if you would like to be able to. Just a little word on SCI for those of you who haven't been here before. The way I like to describe it is founded in 1881, so a long time ago. It was really founded by a whole load of industrialists who decided that they wanted to make sure science was being properly commercialised to the benefit of the UK, because they were worried about how competitive the rest of Europe was getting. Sounds strangely familiar in today's world as well. So still very relevant and still a fascinating organisation, and one which myself and my company are very proud to be members of as well. So do have a look at the website for further information. So on to the main topic of this evening's lecture. It gives me enormous pleasure to be able to introduce our speaker this evening. Professor Sir Martyn Poliakoff comes from a family of scientists, inventors, actors and film producers. His Russian grandfather invented the volume knob on the radio and a method for putting sound onto film in 1899. His father and grandfather, who both were physicists, made radio components in the 1930s for amateur radio builders before diversifying into the first hearing aids for the deaf. In 1956, they launched the first pager, and his father continued in this business until the early 1990s. His mother was a trained actress, and his English grandmother wrote plays. In Martyn's own words, he grew up in a house where everyone expected him to be a scientist, and even had his own lab in the basement, where he conducted some rather dubious experiments, like alcohol distillation, for example. By the age of 14, he had determined that he wanted to become a chemist, as his maths wasn't good enough to be a physicist, but he had an excellent memory, so chemistry was easy and fun, in his own words. With such a rich heritage, it is perhaps not surprising that Martyn would go on to become a leading chemist of our time and a natural and gifted communicator of science. Today, Martyn is a professor of chemistry at the University of Nottingham, where his research focuses on chemical applications of supercritical fluids with a strong emphasis on green chemistry. He has collaborated with many organisations through his distinguished career, including my own company, Thomas Swan. And Martyn will tell you more about this collaboration with my father in his talk. Suffice to say that the two of them went on to construct the world's first continuous industrial phase supercritical CO2 plant, carbon dioxide plant. His YouTube, as I'm sure all of you are aware, YouTube channel, which has over 1 million subscribers, features experiments and anecdotes from Martyn about the elements of the periodic table. And I noticed that one of our young members in the audience has the periodic table on his backpack this evening. So we have certainly a fan in the audience. And his YouTube channel has received praise from the public as well as from Nobel Prize winners, including Roald Hoffmann, who won the Nobel Prize for Chemistry in 1981. Martyn was awarded the CBE in 2008 for his services to sciences and knighted in 2015 for his services to the chemical sciences. Despite this, and on guidance from his children not to be stuffy like other professors and knights, Martyn remains the most wonderfully grounded, accessible and recognisable leaders in the field of chemistry. Ladies and gentlemen, Martyn Poliakoff.
So, I thank you very much, Harry, and I should apologise for you, to those of you who were going to listen to me in February 2017, I had a terrible cold and I was in bed, so I couldn't come. Today I have a slight cough, but I'm better prepared than the Prime Minister, I hope, if things go wrong. My talk, the title, I think, was made up by Sir Geoffrey Allen. So it's really about photochemistry, hence the word light. And it's a joint work from me and my colleague Mike George. And you will hear what George's contribution is as the talk goes on. And what I wanted to do with this talk was to dedicate it to the memory of Tom Swan, Harry's father, who was SCI president from 2000-2002 and who sadly died this January. And the reason why I want to dedicate it is because the research I'm going to talk about, or at least from the point when it becomes clear, was heavily influenced by Tom, not only through sponsorship, but through his enthusiasm and occasional bloody-mindedness. So you will see it was a big influence in my research, and really it was Tom who got me working with the chemical industry, which has been a wonderful experience and continues to be. So, the aim of my lecture is that I want to try and demonstrate that chemists have to help the sustainability challenges facing our society, and I want to show that photochemistry can make an impact and explain how we and our colleagues at Nottingham and our partner universities are trying to contribute. So let me explain the problem. The global population reached 7 billion in 2011, and for those of you who don't know what 7 billion means, it is approximately the number of grains of sand you can put in a pillar box. So this gives you a sort of rough scale. It's a lot. And the population has gone up by 500 million since 2011. So it's increasing fast. And in 2012, I helped launch a report from the Royal Society called People and the Planet. And this report was one of the first that linked population and consumption. And it says that, which is fairly obvious, that all of us in the developed part of the world are consuming too much. But what it also said was that at that time there were 1.3 billion people who are profoundly poor and deserve to consume more. And although this wasn't in the report, I have a working definition of what being profoundly poor means, which is that you can, out of your head, list everything you own. Most people, if you ask them, do not know how many teaspoons they own. I tried this on my group at my university, and one of my colleagues said, put up his hand and said, I only own 5 teaspoons. So I gave him 6 more at Christmas. But so the other point is that people are divorced from, or these profoundly poor people are divorced from modern technology. And I think this picture here from northern Ethiopia that was taken by my son Simon is very symbolic. If you look here, there is a small farm or hut. You can see it's bigger here. And very symbolically, though you can't see it till I highlight, there are 2 electric cables above it. So here you can see there is modern technology and the people in the hut are totally disconnected from it. So the other point is that there are now more people in the world that have that use mobile phones than use toothbrushes. This is also a prompt that you should switch off your mobile phone, and You've all seen a toothbrush, but in case you're one of the people who uses a phone but not a toothbrush, here is one. And the point is a toothbrush has really quite a small number of chemical elements in, perhaps 7 if it has a silicone coating. A mobile phone, on the other hand, contains 40 or 50 elements. Some of them are obvious, like silicon and gold for the contacts. Perhaps less obvious is that you have tungsten, which is the weight that vibrates when you put it on silent, as you should have done now. And many of these elements are becoming scarce. Elements are not like oil. Elements will not run out. But what we're doing is we're digging up elements from relatively concentrated sources and then distributing them across the planet in such a dilute form that you can't easily get them again. And this idea of threatened elements, I think, was first raised by one of Steve Fletcher's colleagues, Mike Pitts, about 10 years ago, and now is really becoming an important issue. So since I come from Nottingham, I have put this into what I call the Robin Hood question, which is how can we provide for the poor without robbing the rich? Because nobody really wants to consume less, or at least they don't want their living standards to drop enormously. And so I think that this is a huge opportunity for chemistry. That is, how can we make more product from the same amount of starting material so that we make chemicals less wastefully, and therefore we can provide more material from the resources that we have. So I haven't mentioned photochemistry yet, so you might feel that you've been cheated. So I want to introduce photochemistry through a very famous paper that was published in the journal Science in 1912 by the Italian photochemist Cimician. As you probably know, the younger people, at least in the audience, that nowadays all scientists want to publish in Science. And this is a very good experimental demonstration that even if you publish in Science, it may take more than 100 years for people to take your paper seriously. And so, but this paper was called The Photochemistry of the Future, and I have one copy if anybody is interested to look at it afterwards. And in this paper, he talked about how he thought in the future industry should be based on light. And the last paragraph says, I believe that industry will do very well from using from this very day forward, that's in 1912, all the energies that nature puts at its disposal. So far, human civilization has made use almost exclusively of fossil solar energy. That meant coal. Would it not be advantageous to make better use of radiant energy? And he talks about setting up solar chemical plants in the desert where you can't do anything else. And so what he was saying in this paper is that coal and also oil will run out, and solar energy will not run out. Of course, if you look at the sun in 5 billion years' time, it will run out, but certainly on the time scales that most of the chemical industry thinks about, the sun will be constant. And the other point is that light can deliver energy selectively to the molecules that absorb it, as opposed to when you heat something with a Bunsen burner, when you heat up the whole bulk of the reaction mixture. And I have quite an old picture here which shows that you can shine light and excite some molecules and not others. Those of you who are keen chemists will realize that it's actually the green cherries that should absorb red light, but for artistic reasons it was easier to shine the red laser on the red cherry. What you can't see in this picture, because it was the days before Photoshop, there was one of my colleagues under here puffing away on a cigarette to make clouds of smoke so you could see the laser beam. And if you want to know how to make a cherry with cake with multicolored cherries, you can ask me afterwards in the questions. So to go back, the other point about photochemistry is that it can promote highly selective transformations. You can often get much more selective reactions with light than you can with heat. And there is a huge body of academic research that has been done in the times, well, some before Chemichun and in the 106 years since. But that academic research has not as yet had much penetration into the chemical industry, actually making chemicals and manufacturing. So what I'm trying to try and explain to you is our strategy for trying to realize Chemichun's vision, and our aim, and I will come back to this project, is to minimize the amount of chemical solvents and processing steps needed to construct complex molecules, and to do this by exploiting light and electricity to promote specific reactions. So in his introduction, Harry mentioned, I'm sorry, I'm getting ahead of myself. What are the problems with photochemistry? The big problem is that when you are trying to do photochemistry, the molecules have to absorb light. And if you have a big vessel, because you want to manufacture on a large scale, the light will not penetrate easily to the middle. So I have a small demonstration of this. I have a scaled-up reactor. I put them here, and I have a colored liquid. And if I put the colored liquid into the reactor, then you can see that if I shine light through the glass part, it goes through, but when I have it with the wine, it is completely absorbed, so the light can't get to the middle. So I have to stay sober in the talk so you can drink the wine.
Outstanding, cheers.
But I need the glass back. I borrowed it from the Royal Society. So what we need is improved engineering to make photochemistry accessible. And what I want to show you is that continuous flow reactors offers a very good way of scaling up chemical reactions, photochemical reactions. So now, Harry in his introduction mentioned supercritical fluids. And if you don't know what a supercritical fluid is, it's a highly compressed gas, CO2, ethene, steam, sorry, I've got ahead of myself, that are compressed till they're nearly as dense as liquids. And when they're compressed like that, they can dissolve solids. And I still find it extraordinary that you can dissolve a solid in a compressed gas. And of course, when you release the pressure, whatever is dissolved precipitates out, either like a snowstorm if it's a solid, or as a rainstorm if it's a liquid. And the more you increase the pressure within reason, the more will dissolve up. So by training, Harry didn't say this, I'm an inorganic chemist. And inorganic chemists are meant to make, or expected to make, new molecules, and I'm very bad at making new molecules. So I suddenly saw an opportunity with supercritical fluids. And particularly, I saw an opportunity to make ethene complexes, which at that time, which was the early 1990s, were interesting. They were chemically interesting. And I had a German friend, who sadly now died, Friedrich Gravels, who was a wonderful synthetic chemist. And he couldn't make these complexes, so I thought I saw an opportunity, perhaps, to show I was better. And so the point with these complexes is that you can make them in solution, but if you try and evaporate the solvent, the ethene that is bound to the metal comes off, so you lose the baby with the bathwater and the compound decomposes. So my thinking was that if you did it in supercritical ethene, which you have very high concentration, if the ethene came off, another one would go on again, so the compound would be stabilized. So I invented this reactor where you have a pump with the starting material and ethene. You go through a cell where you radiate with UV light, so you make the compound, which is then stabilized in solution. You go through a cell so you can monitor the reaction, make sure it's going properly, and then you release the pressure here, and the compound, which is in solution, suddenly goes into the solid. And once it's in the solid, the ethene is trapped, it cannot come off. And so that was the theory. And the critical temperature of ethene is 9.3 degrees centigrade, which is above room temperature in Nottingham most of the time. We don't have very good heating in our building. And so that was the theory, and this is the experiment. Here is the pump for the ethene. The reactant is dissolved here, then it flows past the lamp, through the spectrometer, you release the pressure and collect the product there. So I believe that this is the way you should do synthetic chemistry. You literally turn the handle and the product comes out. And this is the hand of my then student James Bannister with a sample of the chromium pentacarbonyl ethene, which Friedrich couldn't make, you see, or couldn't isolate. And it was only 80% pure, but my point had been made. And then, a few years before that, my student, I'm sorry, I'm going back the wrong way. My then student Steve Howdell, who is now head of our School of Chemistry, so he was my boss, we realized that in ordinary solvent, hydrogen is not very soluble, and you have to mix it really hard in order to get good transport. But in supercritical fluids, as gas is completely miscible with hydrogen, so you get a high concentration of dissolved hydrogen. So Eden, this is specially colored for you. You see there's blue and yellow. When you mix them together, it goes green, just to make the point. And so we exploited this to make the first compound of manganese that had H2 bonded to the manganese, and by using light and reacting it. And then, following our success with the ethene complex, we built a continuous reactor and we isolated, you can't see very much, but some miserable grains of this compound. But this was genuinely the first new compound I had ever made, and I was really excited. And this was in the early 1990s, and then in 1994, the journal New Scientist had an article called Solvents Get the Big Squeeze, which was about supercritical fluids and included some of our work on which I've just described to you. And I was quite irritated. I thought it wasn't a very good article, hadn't done justice to our work and so on. But this article contained a quotation from me which was described, I didn't use this term, but it was in the article, vending machine chemistry. And I apparently said, the chemist will simply press a button and the machine will add the appropriate reagents, supercritical CO2, and pump the mixture into the reactor. And Harry's father, Tom Swan, read this article and got wildly excited. And I don't know how he got my phone number, but he phoned me quite late at night, like 9:30 at night, said he'd read this article and he wanted to work with us. And I was amazed, you see, but then we had long discussions, which nearly broke down, but we agreed that we should work on hydrogenation, adding hydrogen to organic compounds. So this is a sketch of our first apparatus, where the substrate is the material that's going to react, Eden. So you mix hydrogen and the substrate and supercritical CO2. And to begin with, we really did have a stirrer. Later on, we had a more efficient mixer, and then we pumped it through a reactor containing the catalyst, reactant turned to product, and here we released the pressure, and the CO2 went one way, and the product, which was a liquid, came out the other way. And just to give you a scale, this is the size of the reactor. It's about the size of my hand. And so here is a picture of my then postdoc, Pete Licence, who is now also a professor at Nottingham. And the mixer is there, the reactor is there, and the product comes out at the bottom. I used to say that running this machine was as easy as milking a cow. And then one day I was giving the lecture at Moscow State University, and the audience started whispering. And I don't know if you know, but if you're a lecturer, if the audience whispers, it's very distracting. So I stopped and asked them what they were whispering about. They said, "We're wondering whether you've ever milked a cow." So I have never milked a cow. How many people here have milked a cow? Oh, quite a lot. A very talented audience. I've been to some universities where nobody has milked a cow. The answer is that running this is easier than milking a cow. And so then, as Harry said, together with Tom and his colleagues, we scaled this up. So you can see here's the reactor, the size of my hand, and we scaled it up to build a full-scale plant, and the reactor's here with a worker next to him. And this was commissioned in July 2002, that's 16 years ago. Technically, it was a huge success. The product came out so pure that essentially all you had to do was to put it in a barrel and sell it. The problem was that compressing CO2 is expensive in terms of energy, and in 2002, just as this opened, was the time when the price of energy suddenly shot up. So unfortunately, the reactor is not running anymore, but it was a fantastic experience for me, and also, I think, for the company. And building this reactor got me into the Institution of Chemical Engineers, so I felt particularly proud of this. And so now I want to talk about the sort of work we're doing at Nottingham. And I want to remind those of you who are chemists, and to explain to those of you who are not, that oxygen, the O2 that you're breathing in the air, has two unpaired electrons. When people at school draw structures of oxygen, they have nice double bonds, and it doesn't indicate that there are two unpaired electrons. But if you take liquid oxygen, you can hang it between the poles of a magnet. It's magnetic. And in fact, these unpaired electrons is what's stopping all of us bursting into flames, which we would do if oxygen was not so unreactive. Now, if you take a variety of dyes that absorb visible light, like the sort of red color in the seats here, some of these dyes can absorb visible light, and in the right circumstances can transfer the energy to the oxygen and pair up the electrons to make so-called singlet oxygen, which is very much more reactive. If it meets something it can react with, before the electrons have time to unpair. And so this is potentially a very good way of doing reactions, but they involve mixtures of organic compounds and solvent and oxygen, and you do not have to be very technical to realize that this is a recipe for a serious explosion, having oxygen. And so we wondered, my colleague Mike George suddenly realized that you can redraw the diagram that we drew for hydrogen, for oxygen, and oxygen will be very soluble in supercritical CO2, with the added advantage that supercritical CO2, or CO2, is non-flammable. You use it in fire extinguishers. I'm pleased to say you have a fire extinguisher in here, Sharon, over there, though it is a water one, but water is not suitable for singlet oxygen, as I will explain later. So Mike wondered whether we could do reactions in supercritical CO2. Now, singlet oxygen reactions were pioneered by the German chemist Schenck, who was working just after the Second World War, when Germany was, or many of the cities were almost destroyed, and there was a big problem with people having intestinal worms. These are worms inside your stomach, and they could be treated by this compound called ascaridole, which now has been superseded by other treatments. And you can make ascaridole for alpha-terpenine by irradiating it with suitable photocatalyst and oxygen and making singlet oxygen. And here is Schenck in his summer outfit in Heidelberg, making ascaridole using spinach as the leaves as the photosensitizer. Even spinach is the vegetable you don't like. And so we wondered whether we could do the same reaction in supercritical CO2. And I began work in this area with Mike George, and also with the actual work was done by Rich Bourne, who was then a student, and Han Shui, also a student, and Adrian Chapman, who was a postdoc. So you need to have a photosensitizer that will dissolve in CO2. So we use this molecule here, which is called TPFPP, and I can't remember what the letters stand for, but the F stands for fluorine, because fluorinated compounds tend to have superior solubility in CO2. And so this was the reaction again. And the reasons why we were using supercritical CO2 is that it's non-flammable. You have easy product separation, releasing the pressure, and it's miscible with gaseous oxygen. So because Mike and I, by background, are spectroscopists, we began by taking the infrared spectrum of the starting material, and this is the product. And during the reaction, you can see this band going down and that one going up. And you can see all the lines go through a single point. This is called an isosbestic point, and photochemists get terribly excited when they see one of these points, because it means that the reaction is going smoothly from one material to another. It also looks quite nice. It looks like a slightly squashed butterfly. And you can measure the rate at which this is going down and that's going up, and so you can then measure the kinetics of the reaction. For those of you who are chemists, this is quite an unusual reaction because it has zero order, which means that the rate doesn't change as you're using up material, because the rate depends on the intensity of the light rather than the concentration of the products, till you get to right at the end. And the reaction we did was in a small batch reactor, and this is Richbourne. And out of this, we could get 30 microlitres of product. So there's a 2p piece, just to give you a scale. So although this was interesting, it's not very impressive in terms of making compound. So we then decided to scale up the reaction, try and make it bigger using continuous reactor. And so we scaled up by a factor of 3,000 and made 0.2 grams a minute of ascaridole. So in 8 hours, we made 96 millilitres compared to the 30 microlitres before. Ascaridole is colourless, but it's still got the photosensitizer dissolved in it here. It's potentially explosive. So we got quite concerned when we saw this amount. But then somebody in another lab said that they had a use for it and it went away. So we then built more sophisticated reactors. Our reactors use LEDs. These are the similar to the light-emitting diodes that you have in an iPhone, but much brighter. They are the sort of LEDs you get in the headlight of Audi cars, but you can buy them without the car, so that they... and so this is our original reactor, and that's the more modern one. And so you mix CO2 and oxygen and put it through a static mixer. That's a tube filled with sands, so that you make sure it's properly mixed. You then bring in the organic compound, go through a second static mixer, and then it flows through the photochemical reactor. And here you have what is called a back pressure regulator that releases the pressure and the product comes out. And the one of the areas we have been working on is anti-malarial drugs, and which are so-called trioxanes because they have 3 oxygens. And this is some work that was done by our student Jess Bellamy, where you have a flow process. First of all, you take this material and do transfer hydrogenation with magnesium oxide catalyst. Then you have the photochemical step with Singlet Oxygen to make this compound, and then you react it with an acid on supported silica to make this compound. It's not a new compound. These compounds were first made by Axel Griesbeck's group in Cologne. And the reason why people are interested in this is because it has the same chemical structure as is found in the molecule called artemisinin. Artemisinin is, at the moment, one of the best treatments for malaria. This is not stopping you getting malaria, but once you've got it, a way of treating. And some of you may remember that the 2015 Nobel Prize for Medicine and Physiology was won by Dr. Yoyo Tu in China, because she was the first person to isolate artemisinin from the plant Artemisia annua. This was a traditional Chinese treatment for malaria, but she was the first person to find the active ingredient. And so conventionally, the way that artemisinin is obtained is that you plant Artemisia annua, you then let it grow, and you plant it in a tropical climate or subtropical climate like southern China, Vietnam, or Madagascar, and then you cultivate it, you harvest it, and then you extract artemisinin. And this process takes months. Some of you may have seen on the BBC website last night that genetically modified Artemisia has just been announced, which has a higher yield of artemisinin. But it's going to be many years before that can be commercialized. And artemisinin, although it's not a terribly complicated chemical structure, cannot be manufactured from simple chemicals at a reasonable cost. There have been some very elegant chemical syntheses, but they're just too expensive. So the company Sanofi, it's a French-German pharmaceutical company, has developed a process which consists of taking genetically modified yeast, which digests sugar and by fermentation and converts it into this molecule here called artemisinic acid. And the artemisinic acid is then converted into artemisinin via chemistry. So this process takes months, this process takes weeks. And part of this step is photochemistry with Singlet Oxygen. And here's the Sanofi pilot plant. And they've since built a manufacturing plant in Garesio, which is just inside Italy. But if you think about this from a point of view of green chemistry, cleaner chemical reactions, it uses photochemistry, which is really good, but it uses dichloromethane as a solvent, and dichloromethane is somewhat suspect from an environmental or clean point of view, and it uses trifluoroacetic acid, which is highly toxic. And the photocatalyst is not recycled, and it uses a lot more solvents to purify the product. So, Peter Zeyberger's group just outside Berlin did the first continuous process for making artemisinin, and here's their equipment. They got rid of the dichloromethane using toluene, but they still need to purify by recrystallization, and they got 46% yield, and which is slightly lower than the commercial process, but it's already respectable. So we wondered whether we could do it in supercritical CO2, and so this was the work again of Jess Bellamy and Zach Amara and Raf Horvath, who were postdocs with us. And you can see it's a two-stage reaction. It needs visible light to make singlet oxygen, and then an acid where it has a further reaction with oxygen. That's just ordinary oxygen, which is what the 3 is for, triplet oxygen. And we believed that we got 65% yield, which is measured by NMR spectroscopy as opposed to the crystals in the bottle. So this is probably a bit optimistic. But we had quite an interesting result, which was that we ran the reactors before with photochemistry, and then we had a second reactor which had a solid acid for the acid catalyzed step. And then out of the end came this sort of yellowish solid, which was the artemisinin. Artemisinin should be white crystal, so you can see it's not perfect. But what was interesting is that we put our acid in an old photochemical reactor, so we could see it. And these sort of claws are the clamp holding the reactor. And you can see that the dye, the photosensitizer, has been absorbed on the acid. So I suddenly had an idea that perhaps we could make a combined catalyst in which we would deliberately put the photosensitizer on the surface of the amberlist, the solid acid, where they form an ionic interaction. So you would have a dual function catalyst, which could both do the photochemistry and the acid step. And you can see here, amberlist here is a sort of grayish color, and the photosensitizer is purple. And when you mix these together, it goes green, like sort of microscopic frozen peas. And it works really well. So you can have a combined photocatalyst and acid, and out comes the product. But then we had a mad idea, and I'm not sure why we had it, but let me explain why it's mad. We decided to try the reaction in a mixture of ethanol and water. I wanted to do it in vodka, but it's not soluble enough in vodka. You need a higher concentration of alcohol. The reason it's mad is because when you make singlet oxygen, when you pair the electrons, it has to have a short enough, it has to live long enough to meet the molecule that you want it to react with before the electrons unpaired. And it is well known that in water, the OH bonds of water speed up the unpairing of the electrons again. So we decided to make some measurements, and we took our postdoc, Ralph Horvath, went to the lab of Andy Beebe at University of Durham, where he can measure the lifetime of singlet oxygen and hence measure the reaction rates. And he measured the reaction rate of the substrate with singlet oxygen, and the reaction rate is indicated by the slope of the line. If it's steeper, it means react faster, and much to our surprise, the reaction went faster in ethanol water than either in ethanol or in dichloromethane. So we were really excited, and we repurposed our supercritical reactor for pumping ethanol and water through it. We pumped it upwards. When you pump a gas and a liquid together, you have to go upwards rather than downwards. And we put glass beads in the reactor to make sure you had good mixing. And this was work of Zach Amara, student Sam Miller, and Jess Bellamy. And the exciting thing happened at the end. When we started evaporating off the ethanol to get the product, the Artemisinin precipitated absolutely pure. So pure that we could take one of the crystals from our lab 2 doors down the corridor to the X-ray crystallography, and without doing anything except chopping the crystal a bit smaller, they could do the X-ray structure and demonstrate that it was pure. And everything else, that's the photocatalyst, the acid, and so on, just filtered through so it could be recycled. So you have the basis of really quite an exciting process where you put in the starting material, oxygen, you radiate with light, you distill off some of the alcohol, filter off the product, and recycle everything else. And you can also replace the trifluoroacetic acid, which is poisonous, with sulfuric acid. Now, you should not drink sulfuric acid, Eden, but recently there was a paper that showed that there's some bacteria that actually thrive on sulfuric acid, so it's not entirely bad. And this was published 3 years ago in Nature Chemistry. And we made a YouTube video about the this paper, and the video has now been watched by more than 100,000 people. And in July last year, I got an email, which is here, which says, I'm a student at Ly Quai Don High School, Ho Chi Minh City, Vietnam, and I have a strong passion with chemistry, especially green chemistry. I'm having a research in Artemisinin, the anti-malarial drug that I got inspired from periodic videos. And then he said, I'm having trouble with the supercritical CO2 reactor because green chemistry in Vietnam is not strong enough. So I'm asking for your help if you have any spare time. And I think it's really fantastic that I, as a professor in Nottingham, can reach out to a schoolboy in Vietnam and encourage him to become a chemist. So we now come to the way forward, because it's fine doing these sorts of things in the lab, but how are you going to demonstrate that they're valuable to industry? And we decided that this was a huge task which we couldn't do by ourselves, and so research groups need to combine their skills and work together. And so this has led to a project called Photoelectro that is led by my colleague Mike George. And the project it involves collaboration with 3 universities and both chemists and engineers. So there's Kevin Booker Milburn, who's a leading photochemist at Bristol, then Richard Brown, who's an electrochemist in Southampton, and Dave Harrivan, who's an organic chemist in Southampton, and then the three chemists, Mike, Pete, and me in Nottingham, and two engineers, Steve Pickering and Hervé Morvan. And so then there also, we have 24 companies in a stakeholders forum, including Thomas Swan, and we will welcome any other companies that would like to join. So if your company is not represented and you want to join, talk to me afterwards. And it's funded by the EPSRC. And it has three main objectives: to give chemists access to underexploited reactions, designing user-friendly photo and electrochemical reactors, and integrating these into multi-step processes. Now, I don't have time to tell you about all we've done. The project has been running a year, but I'm just going to tell you about a couple of user-friendly reactors to give you a flavor. And the first one is based on a rotary evaporator, which is normally called a rotovap. And lying in the bath one night, I had an idea. If you want the light to be absorbed well in a strongly colored solution, you need a thin film. And I suddenly realized that when a rotary evaporator rotates, it forms a thin film. So we've come up with a photochemical version of this, which we call the Photovap. And so it is a rotary evaporator where you don't need this part at all. And you have two pumps and one flask for the starting material R and one for the product P, and a computer that controls it. So the reactant is pumped into the flask. Then you have lights that switch on and the flask starts rotating. And then when the mixture is cooked, the computer switches this off and pumps out the solution, and you do this repetitively over and over again. And it works really well. With some reactions, we've made nearly 100 grams an hour in a standard rotary evaporator. And we're now working with a company called Ascent to design a lamp, an LED bank, which anybody can use to convert their rotary evaporator into a photochemical reactor. So that's the first of our reactors. The second reactor is slightly more complicated. It's called vortex reactor, and it essentially consists of a test tube, which is cooled, and in the middle of the test tube is a stirrer. And the stirrer is unusual because it is very fat and it is smooth. Normally when you stir things, they have blades like a propeller. This one is smooth, and it has a hole down the middle so you can pump stuff through it. And what happens is that when this stirrer spins, it generates what are called Taylor vortices. These are as a vortex which goes round the stirrer rather like a donut. And so the vortex will take all the solution and stir it up so all of it has a turn in front of the lamp, and you have the lamps on the outside. And then you have a series of these vortices going up the reactor, rather like a series of roundabouts on a motorway. So the molecule goes round there, and then it goes round the other way, and so on. And so our engineering colleagues have done computational fluid dynamics, and you can see here are the vortices that's small, and here they are big. And here's the reactor running with bubbles of air, so you can actually see the lines of vortices going round the stirrer. And I like this picture of the reactor because it looks nice, but you can't really see very much. So the reactor's in here with its bank of lights, and the product is coming out there. And of course, one of the first things we tried it on was Artemisinin, where you can do all of these steps in the reactor as it is running. And with a reactor with really quite a small volume, you can get 5 grams a day out of it. And Mike, Steve Pickering, our engineering colleague, and I have just got a grant from the Gates Foundation to try and develop this to a larger scale so that we could actually use it for manufacturing Artemisinin on a bigger scale. So, just to summarize, photochemistry can give you new transformations, photocatalysis, and improved engineering, we hope, will make photochemistry accessible to all. But most importantly, I feel that together, which means all of us here and chemists and engineers across the world, if we work together, we can realize Chemichan's vision of a chemical industry powered by light. And so I need to thank lots of people. The people in orange are our current group, and those in white above are the people who have worked on this but left. Sam Miller and Amy Flynn are underlined because both of them have had SCI Messel scholarships. In fact, Amy still has one. So thank you very much for supporting them. They are very strong supporters. And Judith, Amy and Connor are our 3 undergraduate projects students who've been working with us in the year. And Steve Pickering is our engineering collaborator. And I should thank the people who have supported our research. And finally, and probably most importantly, I would like to thank our 3 technicians. And it cannot be stressed enough that the whole of the UK chemical enterprise rests on the efforts of our technicians. From schools all the way to industry through universities. It is much easier for a university to replace a professor than it is to replace a good technician. You just need to offer money and a professor will come. But technicians are much harder. And so Rich Wilson and Rich Meehan have made most of our apparatus and continue to make it. And Mark Geiler has worked in our department since he left school. His daughter is now at university. And without these people, we just couldn't do our research. And that message has to be made to not only university administrations, but to government and so on, because technicians are really important. So I should just add that we're successful. We're recruiting PhD students and postdocs. So if any of you fancy a second career, now is the time. And I would also just like to point out that next year is going to be the International Year of the Periodic Table. And I think this is a huge opportunity for all of us to promote chemistry in a very positive way. And I'm on the International Steering Committee of this year. So finally, I would like to end up by reiterating that I want to dedicate this lecture to Tom, and I would not have been doing most of the research that I've talked about without Tom's help and financial support and encouragement. So thank you to your family, Harry, and thank you for listening.
Martyn, thank you so much. And on behalf of SCI, and also I know on behalf of Dad, he would have been very touched that you devoted this evening's lecture to him. I know he enjoyed working with you enormously over the years. So we have something, just a little memento for you here from the SCI to say thank you very much.
That's very good.
We do have some time for questions, we've got some roving microphones around. Please do wait for the microphones before you speak. One over here will take first, and then one behind. You're not allowed to ask about the cherry cake. That's my question.
Okay. Well, thank you very much for an excellent lecture. I was looking at your artemisinin synthesis, and you use ruthenium trisbipyridine
Yes.
in one of your processes. Have you thought about using optically pure material and driving the photochemistry for that process?
I'm sorry, optically.
Optically pure
Yeah,
catalyst.
I think, well, the answer is that in this case you don't need to do that, but people have tried using.
You're starting with an optically pure material.
Yes.
So could you start with racemic material and then drive it through?
Well, I think the problem, I should just explain to Eden what you can get molecules in two forms that are mirror images of each other, like your two hands. And the problem is that if you want to get form one rather than the other, the energy difference is quite small. I think in this case, because you're making singlet oxygen and it is the singlet oxygen that's reacting, that the chirality of the photosensitizer wouldn't make any difference. I think there are various people who have tried to do photochemical, enantioselective photochemical reactions, and we want to do them, but it's not going to be easy because the energy differences are so small. I should say with Thomas Swan we did enantioselective hydrogenation continuously, which was quite successful, and since then we have collaborated with a group in Germany and done it on a kilogram scale. But it's a lot of work to get it to do.
Please wait for the microphone, please.
Keith White, Johnson Matthey.
We need it for the recording.
You need it for the people who are watching on video.
I'm usually loud enough. Keith White from Johnson Matthey.
Yeah.
You gave your researchers academic papers. Have you got any patents to protect it all?
Well, we have patented a variety of things.
Sure.
We got lots of patents with Thomas Swan.
Sure.
I even went to the European Patent Office in Munich more than once to defend the patent.
Great.
It was quite exciting. It's like a PhD viva where they ask the horridest questions they can. It's much more fun attacking somebody else's patent, which I also did once. But the answer is that we are developing some IP with our photochemical reactors. We were about to patent the photovap when we discovered there was something very similar that you could buy on the Chinese website Alibaba, so which was not as elegant as our version, but could be argued was prior art, even though we didn't know about it. So I think obviously there is a balance between patenting and being inclusive.
Especially with the agrochemical one.
Yes. Well, and what with the Gates Foundation, they one of the conditions of the grant is that you should make it freely available to people who might be using your process for making artemisinin. But we're not at the stage yet where we have anything that.
Because in the agrochemical industry, they're all merging. They're getting bigger rather than smaller. So
Yes.
that's a worrying.
Yes.
For your sort of work.
Yes, but I think in our photoelectro project, Johnson Matthey is a partner, and one of our students is sponsored by
Okay.
Johnson.
Thank you very
Matthey.
much.
Any other questions? So, you wait for the mic, please. Thank you.
A very interesting talk. I think I followed most of it. I come from Nottingham, and when I was a young lad, I don't remember the winters ever being as cold as you mentioned.
Well, the coldest. Well, I said 9 degrees, which I mean, well, it's not that the winters in Nottingham were particularly cold. They have been quite cold. But it's that the heating has been almost non-existent, and certainly the coldest it's been in Nottingham when I've been there has been about -10 during the day, and the heating system in our building in whenever it was, I think it was 1981, froze when it was running. And in our lab it was 5 degrees centigrade. In my colleague's office it was minus 2.5 centigrade. So we declared Christmas early. But fortunately the building has been refurbished and it's now actually quite warm. But the Thomas Swan plant, which, because it was hydrogenation, had no walls, got quite cold in winter.
Well, I wanted to go on and mention that I also remember a big pharmaceutical company not far from the university called Boots.
Yes.
And you've not mentioned them at all, as far as I recall. Was there no cooperation with them whatsoever?
Boots, well, the answer is that I've never worked with Boots because, sadly, shortly after I arrived at Nottingham, Boots had a very unfortunate experience with a heart drug, which literally weeks before it was to be released, it was decided that for some reason, which I can't remember, that it couldn't be marketed. And so they sold off all their pharmaceutical research, as well as their production of ibuprofen. Ibuprofen was invented in Nottingham and arguably is one of the greatest blockbuster drugs that's ever been made. So, but there is a new, quite large chemical company, organic chemical company called Signature, which has started up in Nottingham, and some of my colleagues are collaborating with them.
Any further questions?
Yeah,
Could you wait for the microphone?
I never did any chemistry. I never did any chemistries, but I followed your lecture absolutely avidly. But I noticed you're using LED lights.
Yeah.
How much electricity do you need? And is it possible to use solar energy to get the same effects?
Well, that's a very good question. The problem with using, there are 3 problems with using solar energy. The first one is that the sun moves. Therefore, you have to have some quite clever engineering to keep the sun shining on your equipment. The second problem is that the sun, as well as producing light, produces a lot of heat. So you have to filter out that heat, otherwise your apparatus will boil. Probably when you were a child you used a lens to set fire to paper and with sunlight. The third problem, which is perhaps the most serious, is that the sun goes out at night. Well, it doesn't go out, but it disappears. And it also, that there are many days, particularly this year, when it's so cloudy that you get very little light. So I and my colleagues argue, I have several colleagues who think we should be using sunlight directly. I think it may be more efficient to use solar panels to generate electricity and use them to drive lights, because then you don't have to worry about the heat, you don't have to worry about the motion of the sun, and you can run the apparatus at night from mains electricity if you want to. But at the moment, the energy cost of our LEDs are probably less than the energy cost of cooling the equipment. So, but the energy cost is fairly modest compared to the final price of the chemicals, and also is the cost of the solvents and so on that drive up the cost of the process.
Thank you very much.
Any further questions?
You wanted to ask about the cake.
Yeah, how do you make a multicoloured cherry cake?
So like all conjuring tricks, it's a cheat. We went into Marks and Spencer's and bought a cake with red cherries. And at that time, I don't know if it's still the case, you could buy a pot of glacé cherries which were coloured different colours. And we prized out some of the cherries with a penknife and put in the different coloured ones.
On that note, I think we ought to thank our speaker again for a fascinating lecture. So just before I release you all to some drinks and canapes back through where we started earlier on this evening, just to highlight two upcoming lectures. Dr. Alison Treadstone will be talking about overcoming obesity, a taste of things to come on Wednesday the 23rd of May. And Dr. Helen Sharman will be talking about From Mars to the Stars, a chemist in space, on Wednesday the 27th of June. So do mark those in your diary, and hopefully we can welcome you back here again. But for now, there are drinks and canapes served, and again, just a quick thank you to our speaker, and thank you very much.